today let's focus on the beams and thread. So we're going to be doing engineering science and thread. So I've got a question paper here with me. The question paper says that it's June 2022. So the first question that we're going to be calculating is to calculate our reactance, and then after calculating the reactance, we're going to be calculating we're going to be drawing our shear force diagram. So there are two things that I want to highlight before we start calculating. The first thing is to know this formula. The formula is for torque. Torque is equal to force multiplied by the perpendicular distance from the force to another force. So from there, after getting this one for calculating torque, you need to know the formula that says that the sum of clockwise moments is equal to the sum of anti-clockwise moments. Then after that, we go back to our beam. Now let's look at this thing. When you look at it, we have these two things. We call them the UDLs. So the first thing that you need to do before you even calculate, you need to convert these kilonewtons per meter into kilonewtons. So to say that we're going to be removing these meters. How are we going to remove them? By multiplying by the distance of that UDL. The distance of that UDL. So it means the distance of that UDL, it starts from here up until there. So it means it's 4 meters from this side and then 3 meters from that side. So it means the distance is now 7. So we're going to say 6 multiplied by 7. So 6 multiplied by 7, that's 42. Now we have our kilonewtons. And then after that, we also need to convert this one also into kilonewtons. To convert it, we're going to multiply it by the distance. The distance is what? 3 plus 2. 3 plus 2 is 5. So we're going to say 12 multiplied by 5. 12 multiplied by 5 is the same as 60 kilonewtons. Now we're going to start. Already, I thought that we're going to be taking moments about B. So if we take in moments about B, which is this one, it means everything that we're calculating is towards B. B is now our fulcrum, or it's our pivot. So I've made this one to be simple so that people will understand. Now this is our pivot. Let's actually say this is our beam, the whole length of the beam. Now it is pivoted here. So if it's pivoted here, you're going to check for the forces that are going clockwise. And you're going to be checking for the forces that are going anti-clockwise. Now, let's check E. Our E is our reactance. So, if I'm pushing this beam upwards, it means this thing will go this way. So, if it's going that way, it means we'll be having the movement that is going in this direction. And this direction, it's our anti-clockwise. And then from there, if you look at these top forces here, 1, 2, 3, let me not talk about this one, I'll explain it. 1, 2, 3, if I'm pushing this beam downward, because they are going downward, then it means the movement will be like this. So if the movement is like this, it's going in the clockwise motion or clockwise direction. So now we know which forces are going in our anti-clockwise and the ones that are going in the clockwise direction. Now, to start, we're going to be calculating those ones. Now, I want to explain this UDL. The UDL is distributed evenly on the beam. So it means for these first 5 meters, the UDL is being distributed. Now, the weight of that UDL, it acts straight at the center. So if it's acting straight at the center, it means we need the center of this. So the center of this is going to be 5. So we're going to say 5 divided by 2. So if 5 divided by 2, we're going to be getting 2.5 meters. So 2.5 meters, it's somewhere here. I'm just estimating. So if 2.5 is here, then it means here we're going to be having 0.5. So from this 0.5 to the end here, it's 2.5. So we're having 2.5 from here going this side, 2.5 from here going that side. I hope it makes sense. Then from there, we're going to do the same thing in this side. So we'll be multiplying our force now. This one, not this one. This one already converted so that we can calculate as it is in kilonewtons. So let's calculate our return now by taking moments about B. If we're taking moments about B, we're going to check the forces that are going in the clockwise motion. Already, I gave you an example on how to determine the direction. Now, there's another method. This one, if this is the beam, if this is the fulcrum, this one will be going in this direction. This one in this direction. This one also will be going in this direction. But this one will be going in this direction. This one here, if it was this side of this fulcrum, obviously it was going to go in this direction. But now it's in this direction, so it means it's going in this direction. And this direction, together with this direction, it's anti-clockwise. And then 1, 2, 3, they are now going in the clockwise direction. So we now start. We're going to say the 20 kilonewtons multiplied by the distance from these 20 kilonewtons to our fulcrum, which is B. The distance is 2 meters. So we're going to say 20 multiplied by 2 plus, remember it's the sum, so sum it means going to be 80. And then from there, 15 multiplied by the perpendicular distance from 15 to this B is what? It's 3 plus this 2, which is equal to 5. And then after that, we go to this one. This one, hence I said that you're going to be using the total one, which is 42. So you're going to say plus 42 multiplied by the distance from 42. Remember, I said that this thing acts straight at the center. So we need to know the center of this UTI. This is 7. 4 plus 3 is 7. 7 divided by 2 is going to give us 3.5 meters. So it means this thing will be acting somewhere here also. Here is 0.5 for this side. And then from here to this side is 3.5. So we're going to say 3.5 plus 3 plus 2, which is equal to 8.5. Now, there are no more forces that are going in the clockwise direction. So we move to anti-clockwise. Anti-clockwise, we say we have E, which is going this way, and then we have 60, which is going also in the same direction. So you're going to say E, which is unknown now, multiplied by the distance from E to B. The distance from E to B, from here to here is 4. From here to here is 3. And then from here to here it's 2. So you're going to say 4 plus 2 plus 3, which is equal to 9. Plus. The other one that we left is this one. So this one, the distance is from these fours. Remember I said it's 0.5 from this one to this one. So it means the distance already I have it, and then I have that one. So it's going to be 60. 60 multiplied by 0.5. Now, when you get something like that, it's just a matter of solving for x or solving for e. Now, you're going to transpose this one to the other side, it's going to be negative side. And everything you're going to divide it by 9. So let me calculate and see the answer. Okay. Now our answer, it gives us 49.111 kilonewtons. Please don't make the mistake of leaving out the SI unit, because if you leave out the SI unit, marks lost. So after that, since we calculated our E, we're now going to be taking moments about the new fulcrum. Now we're now moving from B. Now this is our fulcrum, so that we can be able to calculate our B. We're now taking moments about it. So it means now the direction might change. In fact, it will change. The distance will remain the same. Now it's only the direction. So So the sum of clockwise is equal to the sum of anti-clockwise moment. Now we're looking for the forces that are going in the clockwise direction. Hence I'm going to do this again. E is now the fulcrum. Now we have forces now. We have this force, this one, and this one. So it means they're acting on top. So it means it's like putting a load on top of the beam. So if I'm putting a load, this thing will go this way. And this direction, it's our anti-clockwise direction. So it means already we have the forces that are going in the anti-clockwise. And then after that, we're going to be checking the forces that are going in the clockwise. There's only one force that is going in the clockwise direction, which is B. So we're just going to say B multiplied by the distance. Distance doesn't change. If you use the distance as 9 here, obviously even here is going to be 9. So the distance from here to here, it's still 9. If you add this, you'll get your 9. Then equal to. Then we're going to be checking our anti-clockwise. Let's start with this one. This one, it's 42. So 42 multiplied by the distance, which is 0.5. The distance from here to here is 0.5. And then from there, the distance from 15, say plus 15 multiplied by the distance is 4. Plus, another distance here, we have 20. 20 multiplied by the distance from here up until here is what? We have 3, we have 4. So it means it's 20 multiplied by 7 plus, we still have this one, which is our 60. So 60 multiplied by the distance from 60 now. Remember I said this thing is 0.5 meters from B, but we need the distance from this 0.5 up until E. So it means from here up until here we have 9, and then we still have this 0.5. So it means we'll be having 9.5 here. 9.5. Now we'll be solving for B. Solving for B, you divide everything by 9. Let me see the calculator. Divided by 9. Then the answer is 87.889 kilonewtons. Now, for you guys in the third, you can calculate it this way, or you can use the shortcut. I'll post another video where I'm going to be doing the shortcut, but if you trust yourself, you can use the shortcut. This one, you can never go wrong, as long as you know what to do. And then after hitting E and B, now we need to check. We need to balance the forces. Now, balancing the forces, we're going to check the forces that are on top. Forces that are on top, we have 60, 20, 15, and then 42. Now, we need to add all those forces on top. When we add them, it's 22, 15, 20, and then 60. When you add them in total, we're going to give you 137. These are the only forces that are on top. Then after that, you need to add the B and E. These are the forces that are going upward, right? They are the forces that are on bottom now. So they are balancing the beam. So it means for this beam to be evenly balanced, we must get 187 when we add E and B. Now E is 49.11 plus B, which is 87.889. Then the answer 137. So it means our beam now is balanced. And once you get this one, now you can start smiling, because it means you have your full 4 marks, or even if they decide to give you 6 marks, you have your full 6 marks. So now, since we have that, I want us to draw the shear force diagram. So drawing the shear force diagram, we're going to do this. Remember, there are many ways to kill a cat. Anyhow, you're going to be doing your thing. As long as you're right, then you'll be fine. To make Now, drawing the shear force diagram, there are two things that you need to know. If you're going to be drawing the shear force diagram, you're going to be having a UDL. A UDL in the shear force diagram is diagonal. It's either it's going to be like this or like this. That's diagonal. But if you don't have the UDL, let's say for instance you have this distance here, there's no UDL, then it means it's just a straight line. UDL, diagonal, and then if there's no UDL, you go straight, right? Now, the same length again. And then this is our A, and then our B. Our UDL must start from A up until B. A here, 0, here, 0. So it means you're going to be starting here and ending it here. If it doesn't end here at 0, then it means something is wrong. Recalculate your things and then maybe you'll get the correct answer. Now the first thing that you're going to be doing, we need to calculate for me. Since we don't have any force here, the next force is this one, which is our tangent. So we're going to say this UDL. This UDL is going downward. So if it's going downward, it's negative 60. We already have the value of that. So if it's negative 60, then we check the next force. The next force is B. Our B is positive. The reason being it's going up. So if it's going up, it's going to be positive B. And our B we calculated it as 87.889. Now, when you calculate this, you get what? According to my calculator, I'm getting 27.889. 27.889. So you go into this one. You're going to measure from here up until where it says 27.889. For me, I'll just get to see if it's here. 27.889 kilonewtons. Then from this one, already we use the UTL because it's this side. So you're no longer going to be using the UTL for this distance, but you're going to be showing it. Don't use the UTL when you're calculating this one. So from B, you say this 27.889, then you're going to say this value subtract 20. So now it's 27.889 subtract 20. We subtract 20 because it's going down. If 20 was going up, it was going to be addition. So 27 minus 88, we know the answer, right? Without even pressing the calculator, the answer is 7.889. Let me write it here so that it's 7.889 kilonewtons. Right? So from here to here, from here to here. Then it's from here to here now. From here to here is just the distance. Now we're going to go 3 meters wide, 3 meters to the next force. So from here to the next force, we're still having our 7.889 kilonewtons, which is this one. Now, for this one, since it's negative, it's 15, you're just going to say 7.889 subtract our 15. When you subtract 15, 7 minus 15 gives us what? A calculator. To me, it gives me negative 7. So it means I'm going from here downward. Negative 7.111 kilonewtons. So this is where my negative 7 is. After that, we now go to the next force. The next force, as you can see, is the UDL before we go to our E. So if it's the UDL, then it means we're going to say 7 minus this one. So 7, already it was negative 7, right? So it's negative 7.111 subtract our UDL, which is going to be 42. Right? So negative 7.111 subtract our UTL, which is 42, then we get negative. So from this one, and then we go to the next force, which is our E, let's just say it goes down there. It gives us negative 49.111 kilonewtons. Then after this, which is this one, you now go into the next force, which is E. E is positive, presently it's going up. So you're going to say negative this, negative 49.111 subtract the next force, which is E. E, we calculated E as 49.111. Then this is equal to 0. So it means from here now, it goes back to this one, which is 0. Now, see that when you're drawing the UTL, since it's under the UTL from here up until there, it means we're going to do diagonal lines. So from here to here is to be diagonally. From here to this one, diagonally. And remember this finished. Then from here to here, there's no UTL. We go 3 meters wide. And that's when we take our 3 meters. Then from here to here already, there's a line like this. Then it's our 15 subtracting, yeah. Then from there, it's under the UTL from here to the next force. From here to the next force. Don't use the UTL as the force. No? So from here to there, it's diagonal again. And then from here to there, it's diagonal. And that's how you're going to be drawing your shear force diagram. You calculate the reactance and then you draw your shear force diagram. Please don't make the mistake of leaving out the values. It might look like it's correct, but if there's no values, there's no marks for it.